Good evening, everyone. Welcome to the Chem Help ASAP evening live stream. So tonight we are going to be talking about heating curves. We will first take a look at just the main features and aspects of a heating curve, and then we will do calculations with the heating curve. Now, this is going to include not only temperature changes, but also phase changes as well. Okay, so let's go ahead and get started. Okay, so here is our first question, and it asks how much heat is required to take 15-gram sample of ethanol from negative 150 to 80 degrees C. Now, again, before we start on this actual problem, here is basically a blank heating curve. Let's just talk about the different parts and how they come together. Okay, so there are parts of the heating curve where you're changing temperature and parts of the heating curve where you are not changing temperature. And these happen at very specific points. So you can see we're starting down here at a low temperature. Again, it's not specified. And then we are heating to this plateau right here. Now, what is this plateau and why does the temperature stop changing? So for this point, which is about right here, you can see that we are still adding heat, but our temperature, again, is not changing. It's not going up, it's not going down, it's staying exactly the same. So what is going on here? Well, what is going on is that heat added to the system is actually causing a phase change. So this first horizontal line or plateau is actually the melting point. Now, that is going to occur at different points for different substances. We tend to know that water melts at 0 degrees C. So if this was a heating curve for water, that would happen at 0 degrees C. We do not yet have the melting point for ethanol, so we don't have a number here to put in it. But that is the melting point. So what that means is this first region right here happened at a temperature lower than the melting point. So we have a solid at this point. So what we did from the beginning of the heating curve up until this phase change was we were taking a cold solid and we were heating it up to the melting point. Then in this second region at the melting point, again, all the energy that's going in is not going to change the temperature, but it's going to change the phase. So we are moving from a solid to a liquid, hence the melting point, right? Okay, so now we have another region of the curve where we're changing temperature. So you can probably guess what this is. So what we've got is we've had a solid, we've melted it. So this third part of the curve is where we have a liquid. And all we're doing from this first point after the melting point all the way up to our next plateau is we are taking that liquid from the melting point and heating it all the way up to the next phase change. Now, the next phase change from liquid to gas is, of course, the boiling point. So here, if I were just to draw a line out, this is the boiling point. And really, maybe I should label these over here on the y-axis. So that one is the boiling point, and this one is the melting point. Okay, you can see here that the amount of heat added at the boiling point is tremendously larger than what is done down here at the melting point. And that is generally true for most substances. It takes a good bit more energy to affect the phase change from liquid to gas than from solid to liquid. Again, usually not always. So this region right here, we'll say we are boiling. We are affecting that phase change. Again, the temperature does not change. It happens all at the boiling point. And then we have this final region once we have vaporized all of our liquid, and we are just heating the gas at that point. So this, we'll call this region 5, and we have a gas. So again, you can see how the regions here where temperature is changing, we have no phase change. So the equation we're going to use in those regions, let's do this in a different color, is Q equals MC delta T, because we have a temperature change. And in this last one, which of course begs the question, for these phase changes where the temperature is not changing, if you try to use Q equals MC delta T, of course your delta T would be 0 and your Q would be 0, which we know is not true because we are still adding energy to the system. We're just doing a phase change instead of a temperature change. So what we need to do at those points is we need to use two changes of enthalpy, the heat of fusion and the heat of vaporization. Now at the melting point, we are going to use the heat of fusion. So our Q here is going to equal our N, our number of moles, times delta H fusion. Again, that is the enthalpy of fusion. That is how much heat is required for the phase change. And the same is true up here for the boiling point. Our Q is going to be, let's put it here, the number of moles times the enthalpy of vaporization. You squeeze that in a little bit there. So you'll notice that we definitely need the mass. We're going to need, so we need the mass. We're going to need the number of moles as well. We're going to need to find our heat of fusion and our heat of vaporization. We are also going to need the specific heats at all three phases. So your specific heat for your solid, say, is not going to be the same for your liquid, is not going to be the same for the gas. So you want to make sure that you have all of the data that you need for all of these calculations. Okay, are there any questions on, again, just the basic features of the heating curve? Okay, good. I'm glad that volume is good. Okay, great. All right, let's go on. And I have gathered up all of the information we need, and it's a lot of information. Let's put it all together and let's actually calculate the heat required to take this 15 grams of ethanol from negative 150 to 80 degrees Celsius. Okay, here we go. And this is kind of small. So there we go. That's a little bit bigger. That's a little bit better. All right, so I still have my problem here because I need to know what's going on. So let's just take a look at the data that we have. You can see we have the molar mass. We've got the enthalpy of fusion and the enthalpy of vaporization. We know where the melting and boiling points are, which is key, as you'll see. And here you can see we have the specific heats for all of the different phases. So we have all of the information we need. Now we need to figure out how to put it together and what all we need, because we're going from negative 150 to 80 degrees C. Now, I don't have the melting point and boiling point of ethanol memorized. So what I need to do first is to decide how many phase changes are we going through, if any. So if we take a look here at the melting point or the freezing point, of course we're heating, so I refer to it as the melting point. You can see the melting point is at negative 114. So we are starting below the melting point, which means we are starting with a cold solid. Now, what about the upper end? Are we ending in a liquid? Are we ending in a gas? What are we doing? So we're heating to 80 degrees Celsius. You can see the boiling point is 78. So we are heating just beyond the boiling point, which means we are going to end with a vapor or a gas. So we are going to move through solid, liquid, and gas for this heating curve. So we are going to move through all 3 phases, which means we will have 5 different calculations to do. No, to take that back, we will have 6 because we'll have 1 at the end. But if we go back just really quickly and take a look at this curve, there are 1, 2, 3, 4, 5 pieces of this curve. We're going to do all 5 of those calculations, and then we will add those numbers together up at the end. That is the 6th calculation. So, this is going to take some time, but that's all right. We can do this. Let's get started. Okay. So again, our first step is we're going to take our cold solid and we have to heat it to the melting point. All right, that is a temperature change. So we are going to use Q equals MC delta T for this. But let's be careful. This is our step 1. We'll call this Q1. Remember, this specific heat needs to be the specific heat for the solid. So I'll put an S down here for solid. And we need the temperature change. All right, well, the problem gave us our mass. That's 15 grams. Oops, that decimal didn't show up. Now I need the specific heat again for the solid. That is 2.42. And that is joules per gram times degrees Celsius. And now I need the delta T for this. Again, I'm starting with a cold solid and I'm going to the melting point. So my melting point occurs at negative 114.1. That is going to be my final temperature for this step. And I am starting at, according to the problem, negative 150 degrees Celsius. So that is quite cold. You know, I think I'm going to change that to brackets. That makes it a little bit better. Okay, so just mathematically here, obviously that is going to change to a plus sign. Let's double check and make sure that all of my units cancel. So my grams will cancel and my Celsius will cancel. So this will give me joules coming out. Okay, that all looks good. So if we actually do this calculation, we get a value for Q1. And our Q1 is 1,303.2 joules. Okay, so that's our first step. We got 4 more to go. All right, so our second step. Remember, our second step is our phase change. Let's just take a quick look back at our heating curve. So our step 2 here is our phase change. So we've taken our cold solid, we have heated it to the melting point, and now we need to do the phase change. Again, no temperature change happens here. Let's go back to our calculations. So in this case, for the phase change, we need the heat of fusion. And we do have that. You can see we have the heat of fusion right here. And see how the units are in kilojoules per mole. This is why we multiply by mole. So my equation is going to be Q2, because this is my second step. My number of moles times my enthalpy of fusion. Now I haven't yet calculated my number of moles, so before I can do my calculation number 2, I need to do a quick calculation to convert from grams to moles. Well, the nice thing is I do have the molar mass right here. So if I have 15 grams of ethanol, let's just do a quick conversion. The molar mass is 46.069 grams per 1 mole. And that will give me 0.3256 moles. So we'll just keep that up there because we're going to need it when we do the boiling point as well. Okay, so my N is my 0.3256 moles. And my heat of fusion is 5.02. And my units are kilojoules per mole. Again, I get my units just from the table right here. It told me that it was kilojoules per mole. Usually it's kilojoules per mole, but you might find some heats that are kilojoules per gram. So you just want to make sure you look carefully at your table, look where you're getting your data, and don't just pull the number, but make sure you pull the units as well. So you can see in my calculation, my moles are going to cancel, and I'm going to be left with kilojoules for my heat, which is fine. And so when I do this, I get a Q2 of 1.635 kilojoules. All right, so that's step 2. Let's go back to the heating curve. We've taken care of step 1, step 2, now step 3. So we took our cold solid, we heated it to the melting point, we melted it. Now we have a liquid at the melting point, and we're going to go all the way up to the boiling point. So that is our step 3. Because we've got a temperature change, we go back to Q equals MC delta T. Okay, so this is step 3. I'm not sure if I'm going to be able to put everything on this page, but I've got a second page ready. Okay, so step 3, this will be Q3 equals mass. Okay, so again, I need to be careful about which specific heat I use. I am in the liquid phase now, so I'll call that specific heat of liquid times the delta T. All right, I have my mass. That is 15 grams. Find my specific heat for liquid is 2.44, and that is joules per gram times degrees Celsius. Now for my delta T, again, if you think to your heating curve, we're going from the melting point up to the boiling point, so that is our delta T. So we are ending at the boiling point for ethanol, which we check our top table, you can see is 78.2 degrees Celsius. I'm going to have to squeeze this underneath. Minus, again, we started at the melting point, that is negative 114. And that is my delta T for this section. So again, let's make sure that units cancel. The grams are going to cancel. The Celsius is going to cancel. And I'm going to be left with joules for this Q3. So I have Q3 is going to be 7038.2 joules. Now you notice when I'm doing these calculations right now, if you're concerned about sig figs, don't worry about sig figs at this point. I would say do those at the very end. Carry more sig figs forward than you think you need to, because there are a lot of calculations here. If you start doing a lot of rounding, then you're going to start to introduce rounding error before you get to the end calculation. Okay, that is our third step. So we're halfway there. Now let's look at our fourth step. Again, let's go back to our heating curve just so we know where we are. We took our cold solid, we heated to the melting point, then we melted it. So now we have liquid at the melting point. We heated it all the way to the boiling point, and now we are going to do another phase change. So we're going to keep putting heat in. There's no temperature change, and we are going to take that sample from a liquid to a gas. We are going to vaporize it, or boil it. We kind of use all these terms interchangeably. So for this one, again, not a temperature change. My Q4 is going to be my number of moles times my enthalpy of vaporization. And I'm going to get this from my table. Let's see, there's fusion. Here is my heat of vaporization. Of course, I've already calculated my number of moles up here. 3256 moles, and heat of vaporization is 38.6. Again, this is kilojoules per mole. And like always, I like to make sure that my units cancel, and I'm going to be left with kilojoules. Okay, so Q4 is 12.57 kilojoules. And you can see how much bigger it is than the Q2. Again, usually for most compounds, going from the liquid to the gas phase requires a lot more energy to be put into the system. Okay, so that's for, we're not there yet because our boiling point occurred at 78.2, but our problem wants us to go to 80. So we need to go just a little bit past the boiling point. If we go back and take a look at our heating curve, so here's where we have vaporized our sample. So we're just doing a little bit here to get it up to 80 degrees Celsius. Okay, so step 5, our Q5 is, again, we go back to Q equals MC delta T because we have a temperature change here, not a phase change. And for this one, remember, we are in the gas phase, so we want our specific heat to be the specific heat for the gas. So if I come down to my specific heats, you can see my specific heat for the gas is actually much larger. And I'm going to have delta T. So this is my 15 gram sample, my specific heat, grams times degrees C, and my delta T. So I am going to end here at 80 degrees C because that's what my problem told me to do, to end at 80. Oops, I'm going to have to switch down here. And remember, for this, I started at the boiling point. That was my last calculation here, was a phase change at the boiling point. And so that was at 78.2 degrees C. So I'll just kind of squeeze that in there. All right, again, let's check units. My grams will cancel, my Celsius will cancel. I'm left with joules. So my Q5 is going to be about 1,000 joules. Okay, so we're almost there. We have calculated the Q for each of our individual steps. Now we need to add it all together, and that will tell us how much heat is required to take this 15 gram sample from a very cold solid all the way to a hot gas. Now there's a little bit of a problem that we're going to have to deal with. When I used Q equals MC delta T, all of my answers came out in joules, which is totally fine. But when I did my phase changes, I got my answers in kilojoules. So I cannot add these as they are. I need to convert either the joules to kilojoules or the kilojoules to joules. Now, because this is generally a larger number, I find it easier to convert the joules to kilojoules. So let's do that very quickly before we add everything up. So I'm just going to take my Q1 and I'm going to convert to kilojoules. I'll do the same thing with Q3. And that is now kilojoules, and also for this last one, that is kilojoules. Now, because I'm running out of space here, I am going to go ahead and go to our blank page. I thought I might need a little bit more space. And now we're simply going to add everything together. So my Q total is going to be my Q1 plus my Q2 plus my Q3, then my Q4, and finally my Q5. So I'm just going to pull the numbers from the previous page, put them down, and add them all up. So we have 1.3032. Again, remember this is all kilojoules. It's always nice to double check and make sure that you've got the same unit for everything. Again, you can convert everything into joules and add it up. Then you might want to go to scientific notation, which is perfectly valid. Or in this case, I chose to go to kilojoules. 635, that is a 5. Again, kilojoules. Let's keep going. That decimal is having some trouble. Okay. 7.0382 kilojoules. I don't know if I'm even going to get this on one line. I should have started farther away. And I have my last Q5, which I am just going to wrap on down here. So those are all of my Qs. Again, I'm just going to add these all together. And I get 23.5 kilojoules. And that is how much heat it takes to take a 15 gram sample of ethanol and go from negative 150 all the way to 80 degrees Celsius. Okay, any questions? No questions. I know that's a long problem, but it's all right. We're going to practice this one more time, but with a different compound. Okay, so here is our next problem. Now we are doing what is called a cooling curve. It's the same thing. We're just doing the reverse process. So the question is, how much heat do we have to remove? We still, have a 15 gram sample, but now we're dealing with benzene. We're going from 95 to 3 degrees Celsius. This cooling curve has the same features as the heating curve, except this time we're starting with a hot gas up here. So our Q1, our first section, we're going to take that hot gas and we're going to cool it down to the condensation point, which is the same thing as the boiling point, but because this is a cooling curve, we are going to condense the gas, not vaporize it. Okay, so we had a gas up here. We've cooled it down to the condensation point. This is section 2. And of course, this occurs at a very specific temperature. I will go ahead and label it just as the boiling point here. So that's usually the convention. But when we talk about a gas going to a liquid, that is condensation, obviously not boiling. All right, so this phase change occurs. So we take the gas, we then condense it down to a liquid, and then we have a liquid at the boiling point. So we want in our section 3, we're going to take that liquid that's at the boiling point and cool it all the way down to the freezing point. Again, because we're cooling, we're going to call this a freezing point instead of a melting point, but they occur at the same place. And in section 3, just like before, we have a liquid. And this plateau here does occur at what traditionally is called the melting point, but we are freezing this because we're going from liquid to solid. Oh, this is section 4. And then depending on how cold we go, you might take the solid at this point and cool it down even farther. And that would be the tail end of the curve. This is section 5. So just like before, let's specify what equations we're going to use in the different sections. So in section 1, when we've got the gas and we're just cooling it down to the condensation point, that is a temperature change. So we use our good friend Q equals MC delta T. Then at the condensation point, again, we need to use that enthalpy of vaporization. And we're going to use Q equals N times the enthalpy of vaporization. For our section 3, we're taking our now liquid and we're going from the condensation point all the way down to the freezing point. It's a temperature change, so we go back to Q equals MC delta T. And for our section 4, we've now got the liquid down to the freezing point. We need to actually freeze it, so we've got another phase change. So this time we need the enthalpy of fusion. So we're going to, I think I'll write it up here, use Q equals N times the enthalpy of fusion. And then finally, once we've taken the liquid, we have frozen it at the melting point, and we're going to cool it down even farther. That is a temperature change. So we go back to Q equals MC delta T. So what we're going to have to do is we're going to have to take a look at the information on benzene and decide how many of these steps do we need to do. Are we going to go through all three phases just like we did with ethanol, or are we only going to do part of the heating curve? So let's take a look at all of the information for benzene. So here we go. And I think I'm going to zoom this in too, because again, getting all these calculations on one page is a bit of a challenge. But let's take a look at what we've got here. So we're going to go from 95 to 3 degrees Celsius. So I'm wondering if we're actually going to hit the solid phase, but let's see. So starting at 95, are we above the boiling point? So benzene here is our, yes, we're definitely above the boiling point because it boils at 80. So then the question is, at 3 degrees Celsius, are we in the liquid phase or are we in the solid phase? So we need the freezing point, and our freezing point is just a bit above. So yes, we are going down lower than the freezing point. So we are doing the same thing, except now we're cooling. We're starting with a hot gas. We're going to condense it to a liquid. Then we're going to freeze it to a solid, and we're going to cool the solid just a little bit. And we also have, of course, our specific heats for all of our different phases, because that is important when we do our Q equals MC delta T. All right, before I jump into the actual calculations, okay, just wanted to make sure that there were no questions about this. So I'm going to organize this the same way with Q1 through Q5, but in this case, I think I will actually go ahead and calculate my number of moles before I start, just so that I have that ready to go. So I have, again, a 15-gram sample of benzene, which is C6H6. And my molar mass is given to me here, which is fabulous. So I can just do a quick conversion. And that will give me 0.192 moles. Okay, you didn't have to do that to start with, but I just kind of like to have all of my information ready to go. Let's go ahead and start with our Q1. So our first step, remember we're taking this hot gas and we've got to bring it down to the condensation point, which is the same thing as the boiling point. This is a temperature change. We've got a gas, so we need to make sure we use the specific heat for gas. And then our temperature change is going to be from the starting point to that condensation point. So our mass is 15 grams. And my specific heat for that gas is 1.05 joules per gram times degrees Celsius. And my delta T, so I'm going down to the condensation point, so I'm going to end at 80.1 degrees Celsius, and I started at 95. Okay, sorry, this is Q1. I forgot to label that. So my Q1 is going to be 234.7 joules. Again, we didn't do this before, but you can see the grams cancel and the Celsius cancel, so I'm left with joules. Now, one thing I am leaving off here is this is actually a negative number because we are not adding heat to the system, we are pulling heat out of the system. But I'm not going to worry about the sign convention while doing all these intermediate steps. I will worry about the sign convention at the very end of the problem. So I'm going to keep all of my Q's positive for now so that I can add them up easily, and then we'll talk about the sign convention at the end. So I just wanted to add that in. Okay, so we took our hot gas and we brought it down to the condensation point. So let's go back to the heating curve just so we know where we are. So we've done this small section here. Now we need to condense this gas from a gas to a liquid. So this is our Q2. So our second step, our Q2. This is a phase change, so we're not going to use MC delta T. We're going to use the number of moles. times the heat of vaporization. So I have already calculated my number of moles. I'm just going to put that in here. That is moles. And my heat of vaporization for benzene is given right here. That is 30.5 kilojoules per mole. As always, making sure that moles are going to cancel. I'm left with kilojoules. So my Q2 is 5.86 kilojoules. Okay, great. Now we need our step 3. Let's go back to our heating curve just so we know where we are. We took our hot gas, we brought it down to the condensation point, we condensed it into a liquid. So now we're going to take this liquid and come all the way down to the freezing point. So we're back to Q equals MC delta T, which is everybody's favorite. And in this case, because I'm in the liquid phase, I need to make sure that I use the specific heat for the liquid. All right, so I still have 15 grams. My specific heat for benzene in the liquid phase is 1.70. Again, that is joules per gram times degrees Celsius. And my delta T for this is I'm starting at the boiling point or the condensation point and coming all the way down to the freezing/melting point. So I have my melting point here at 5.5. And I started at the condensation point, which is 80.1. Again, making sure units, grams are going to cancel, Celsius is going to cancel. So this will give me Q3 in joules. Oops, I forgot to label Q3 up there. All right, so Q3 is 1902.3 joules. All right, let's go back to the heating curve. Let's see where we are. We took our hot gas, we brought it down to the condensation point, we condensed it, we took our liquid, we took it all the way down to the freezing point. Now we need to freeze. So we've got a phase change. We're back to using our number of moles, and this time we're going to use the heat of fusion. Okay, step 4. Q4 is going to be my number of moles times my heat of fusion. All right, so here is my number of moles and my heat of fusion for this. There's vaporization. Heat of fusion is 10. Again, that is kilojoules per mole, which means that my moles will cancel. I'm left with kilojoules, which is great. So Q4 is 1.92 kilojoules. Okay, back to the heating curve one more time. Took our hot gas, we brought it down to the condensation point, we condensed it, we took our liquid and brought it all the way down to the freezing point, we froze our sample, and now we're going to take our solid and we're just going to cool it down to where the problem tells us to cool it. So step 5, Q5, we're back to MC delta T, but in this case, again, we're in the solid phase, so our specific heat needs to be for the solid. We still have 15 grams. Let's get the specific heat for the solid is 1.51. And that is joules per gram times degrees Celsius. Now for our temperature change, remember we've been at the freezing point and now we're going down to, the problem tells us 3 degrees Celsius. So we will end at 3 degrees Celsius and we started at the freezing point, which is 5.5. Okay, make sure grams are canceling, Celsius is canceling. I'm going to get this Q in joules. So Q5 is 56.6 joules. So now, again, just like with the previous problem, I have my heats for all 5 of the steps, so I need to add them all together, and that tells me how much heat is going to be removed from this system. Now, just like the previous problem, when I use Q equals MC delta T, I get these out in joules, but of course my phase changes come out in kilojoules. So again, I'm going to convert into kilojoules because these are larger numbers. Let's go ahead and do that right here. So there is Q1 converted into kilojoules, Q2 in kilojoules, and Q5 also in kilojoules. And just like before, I need some more space because these problems take a lot of space. So I have my Q total is going to be my Q1 plus my Q2 plus my Q3 plus Q4 and finally Q5. This time I'm going to start a little bit farther over to the left, see if I can get everything to fit. So Q total, here we go. These are all in kilojoules. Almost there. That is a plus. And our Q5 there we go. Okay. Adding all these together, I get a Q total of 9.97 kilojoules. Now, depending on the problem, because this is heat removed, it's very often shown with a negative sign. However, I've seen it a couple of different ways. It really depends on what the problem asks and also what your teacher or your professor wants. So sometimes people will say 9.97 kilojoules removed and they won't make it negative. Other times they'll just make it negative and they won't specify that it is removed. And sometimes you'll see both the negative and you'll see that it is heat removed. So it really just depends on, for your specific class, what does your teacher or your professor want you to do in terms of the positive or negative sign? But because this is heat removed from a system, your Q's are going to be negative. Just like you saw when we calculated Q using Q equals MC delta T, those all came out negative, again, because we're removing heat from the system. But when you're using your heat of vaporization and your heat of fusion, it's up to you to determine if you are adding heat in and it's positive or if you're removing heat and it is negative. So let's make sure there are no questions. So there's a question. The mass remains the same after the vaporization. Yes, it does, but that is an excellent question. So in this heating curve here, for any of the heating curves, whatever mass you start with is the mass you finish. So theoretically, these phase transitions would maybe be happening in a closed container so you don't lose any mass. Obviously, if you did this just like out on the bench top and you vaporized your sample, then you would lose it to the atmosphere. So if you are actually doing this in lab, you want to make sure you have a closed container. Otherwise, that is going to change your calculations quite a bit. So yeah, that is a very good question there. Okay, if there are no other questions, then I think we've done enough calculations for tonight. We have certainly gone through many, many of them. This is another great example of watching your units as well, because the temptation is to get all your Q's and just throw them all in the same pot and add them together. And then, of course, you don't end up with the right answer, which is extremely frustrating, especially when you're doing like a test and you, of course, want to get the right answer. So make sure you watch those units. All right. Thank you so much for joining us. And as always, feel free to email me if you would like to see another topic covered. Good night.